These are the two problems I left you with at the end of the last video. For this first one, since 16 is a power of 4, it's just 4 squared, I can keep the left-hand side as it is. 4 to the 3x minus 1 equals, I'm just going to rewrite that 16 as 4 squared. Then that's to the 5x plus 2. So then 4 to the 3x minus 1 equals, now when I'm taking a power to a power, I know to multiply the powers, and I just need to distribute the 2 to both parts. So this becomes 4 to the 10x plus 4. If 4 to this power equals 4 to that power, the exponents are the same. So 3x minus 1 equals 10x plus 4. That becomes a nice linear equation. So we'll have negative 1 equals 7x plus 4. Negative 5 equals 7x. X equals negative 5/7. So that would be my answer to this first equation. Okay. Now the second equation, which is one of the ones from their homework, is a little bit more challenging because 1,000, which is my bigger base, isn't a nice integer power of 100. I could write it as a fractional power of 100, but I think it's easier to recognize that both of my bases, both 100 and 1,000, are just powers of 10. So I'm going to rewrite both sides as a power of 10. So 100 is 10 squared, so that's going to be 10 squared to the 3t minus 5. 1,000 is 10 cubed, so that's going to be 10 cubed to the 3 minus t. Now on both sides I have a power to a power, so we just multiply the exponents. So we're going to have 10 to the 6t minus 10. Again, don't forget to distribute that 2. Now, if you find it helpful to write 10 to the 2 times 3t minus 5 as a preliminary step and then distribute the 2, you can certainly do that. Okay, I'm just going straight to distributing things, but if you find it easier to write that out first, definitely worth the time. Okay. All right, so on the right-hand side, it'll be 10 to the, we're multiplying 3 times 3 minus t, so that's going to be 9 minus 3t. If 10 to that power equals 10 to that power, then 6t minus 10 equals 9 minus 3t. The exponents must be the same. So I'm going to add over those 3 t's, so we'll have 9t minus 10 equals 9. Let's add over the 10. 9t is 19. T is 19 ninths. All right, excellent. Now, the problems we've done so far, we've been able to rewrite both sides with a common base. We've had to rewrite one or both sides, but we've been able to do that. Now, let's suppose I had 3 to the 5t equals 7. Okay? So the right-hand side, I didn't even write that as an exponential expression, but I could think of that as it's 7 to the first. Now 7 is not a nice, neat power of 3. It is a power of 3 because I could take the log base 3 of 7. That's the exponent I would need to get 7. But that's not a nice, neat integer. I'm going to really struggle to try to rewrite 7 as a nice power of 3 that I know off the top of my head and can express without using logs. Okay. And I don't see my two bases, my 3 and my 7, as particularly having anything in common. I don't see a nice common base that I could write them both as integer powers of the same thing. Okay. So here's a situation where I'm not going to be able to conveniently rewrite both sides in terms of the same base. So here's where I'm going to use logs. I'm going to use logs to undo exponents. So I want to solve for this exponent. Now, you might think I should use the log base 3. If I took the log base 3 of both sides, then the left-hand side would just be 5t. It would just be that exponent, and then I could solve for t by dividing by 5. The problem is, I don't have a log base 3 key on my calculator. So if I wanted to get a decimal approximation of that answer, I could get the exact answer in terms of the log base 3. But if I then wanted to get a decimal approximation using technology, I'd need to use my change of base formula, which I haven't bothered to memorize. Because it's a lot easier to just not use the log base 3. I have two common bases that I use all the time and that every scientific calculator is going to come with a key for. Base E for the natural log and base 10 for the common log. So if I need to use logs, I'm going to ignore the base that I have and I'm going to use either the common log or the natural log every time. That may sound weird initially, but let's do it and let's see why. Now, it doesn't really matter whether I use the natural or the common log. Okay? In a lot of the homework, the book says express your answer in terms of either the natural or the common log, so you get to choose. And then they ask you to use a calculator to get a decimal approximation of your answer as well. Okay? Generally speaking, I will ask you to express your answer, and I will specify either the natural log or the common log. That way I'm testing you on vocabulary at the same time. So let's express our answer in terms of the natural log. All right, that means I'm going to take the natural log of both sides. Okay, so in math we do this all the time. We have an equation, we do the same thing to both sides. If this equals that, and I change this, but I change that exactly the same way, they're still going to be equal to each other. So, you started out with basic algebra, you'd maybe add 2 to both sides. As you move through math, you start doing more and more complicated things to both sides. You can take the log with the same base of both sides of an equation. Okay. Now, it does need to be that what I'm plugging into the log is positive, but I can see it is. 7 is positive, and this is equal to 7. So both sides are positive. I can, in fact, take the log of both sides. Okay. Now, this is the log base E. I'm plugging in the exponential function base 3. They don't just undo each other. They're not inverses because they don't have the same base. But I can use my rule of logs. My rule of logs say when I have the log of something to a power, I can bring that power down. So this is 5t times the natural log of 3 is equal to the natural log of 7. Okay. So the variable was up there in the exponent position. By taking the log, I'm able to bring it down to ground level. Now, this is super corny, but I love corny mnemonic devices for remembering what I need to do. So I like to think of it this way. The exponent is way up there. I can't reach it. So I need to haul over a log so I can stand on the log. Here's my log. I'm going to stand on that. And when I stand on the log, now I can reach, I have very long curvy arms, now I can reach that exponent and bring it down and put it on the ground. Super corny, but I like it. Okay, once the t is on the ground, now I can solve for it. Because let's see, what am I doing to t here? I'm multiplying it by 5, and I'm multiplying it by the natural log of 3. The natural log of 3, this whole thing, ln3, that is one number. Okay. It's kind of a messy number because it's an irrational number. If I plugged that into a calculator, it would fill up the screen with digits, and I'd know that those digits actually went on and on and on, and the calculator had just rounded to the last place that fit on the screen. Okay, but this is just a number that I'm multiplying by. What do? If I'm multiplying t by something and I want to solve for t? Divide by that. So I'm going to divide by both of these. I'm going to divide by 5 and by the natural log of 3. So I'll divide by 5, natural log of 3, and I will get t is the natural log of 7 divided by 5 times the natural log of 3. That is my exact answer. Okay. Now, as you're doing the homework, the book asks you to give your answer in terms of either the natural log or the common log. If we had taken the common log, all we would have is instead of ln, we would have log, log in both places. That's not to say that the natural log of 7 and the log, the common log of 7 are the same, but the ratio of them would be the same. Okay, kind of an interesting fact. Okay, the book will also ask you to take out a calculator and get a decimal approximation. And I just want to point out that you need to be careful as you enter this in, because I will usually enter a fraction as a division problem. So I would enter this into my calculator as the natural log of 7 divided by, but now it's being divided by two things. It's being divided by 5 times the natural log of 3. That needs to be in parentheses. So 5 times ln 3 needs to go in parentheses if you're going to enter that in as a division problem. If you leave out the parentheses, then what it's going to do is move that natural log of 3 to the top. Because the rule for order of operations is not multiply first and then divide. PEMDAS is a 4-letter word. You do parentheses, you do exponents, then you multiply and divide, not M first and then D, not multiply first and then divide, but multiply and divide left to right. So if I didn't have these parentheses, I would divide by 5, and then I would multiply the result by the natural log of 3. Okay, so do make sure that you enter that in correctly. Let's go ahead and do that. So natural log of 7 divided by parentheses 5 times natural log of 3, close parentheses, equals. All right, and so I get that that's approximately 0.354. Okay, I rounded to 3 places. If I ask you to do that. Now, I wouldn't ask you to do that on a timed exam or quiz because you can't have a calculator there. On a take-home quiz, I might very well ask you to do that, and then I would specify what place to round to. Okay, but on timed exams and quizzes, I will simply say, express your answer in terms of the natural log, or I might say the common log, and this is where you would stop. You would give me the thing you would plug into the calculator to get a decimal approximation of things. Okay, this is the exact answer. That's what I want. But it is kind of nice to use the technology to get some sense of how big the number actually is. That's especially nice when we're looking at application problems. If we're saying, like, how long will it take for my investment to double? You know, and I have something like this. It's like, well, how long is that? How many years do I have to wait? It's nice to have a decimal approximation and say, oh, 10 years. Okay. All right. So there's that. We'll do more of this in the next video.